Number 1A, the list below shows some SI quantities. Underline the quantity that is not an SI-based quantity: charge, current, length, time. So I will underline this one because charge is not an SI-based quantity. If current has length as well, time as well, time SI-based quantity is second, length meters, current amps, right? B, a square solar panel with sides of length 1,300 millimeters is shown on this figure 1.1, right? So incident light towards, downwards, and this is two solar panel, and okay, the side length 1,300 millimeters. Light is incident normally on the solar panel. 1. The power of the light incident on the solar panel is 750 watts. Calculate the intensity of the light. Right. Intensity of the light, I will start with the side. I'm going to convert into meters. So 1,300 millimeters, if you convert into meters, will be 1.3 meters. Okay. So this one, 1.3 meters. And area of that solar panel area is 1.0 times 1.3 or 1,300 millimeters times 10 power minus 3 meters. Meter, yeah, if squared, okay, means squared here, yeah, because area. Right, so the intensity we can determine through this formula, I equals P over A. Power is 750 watts, while area this one, or 1.3 times 1.3 meters squared. But I would like to write in this one. And if you convert, becomes 750 watts, 1.3, 1.3 meters squared, and the result is 440 watts meter power minus 2. Wait. Okay, so there's the solution here for 40. The percentage uncertainty in the incident power is plus minus 3%. There is the uncertainty in the length of each side is plus minus 5 millimeters. Calculate the percentage uncertainty in the intensity of the light. Right, so the percentage uncertainty is this one plus minus 3% plus 2 times there are two sides plus minus 5 over 1,300, okay, times 100%. And if you calculate it, the result will be plus minus 4%. So 4% here. The useful power output of the solar panel is 160 watts. Calculate the percentage efficiency of the solar panel. Okay, so percentage efficiency. Formula is useful output power over total input power times 100% because percentage, and it is 160 the output over while the input is 750, and the result is 21%. So 21%. Another square solar panel is placed so that light of the same intensity is incident normally on it. The new panel has shorter sides than the original panel. Uh, so it's smaller than the original panel. The new panel has the same power output as the original panel. State and explain whether the efficiency of the new panel is greater than, less than, or the same as the efficiency of the original panel. Okay, so the new panel area, I'd like to write in here the new panel. The new panel area is less than original panel area. Okay, why? Because based on this information that the new panel has shorter size than the original panel. So it means the new panel area less than original panel area. So it's implicated on input power. So the input power, regarding the input power of the new panel is less than the input power of the original panel. Why? Because it has it has shorter sides than original panel. All right. So now we can that through this information we can state that I'm writing here that the new panel more efficient than original panel original panel, or we can state that uh, efficiency of the new panel is greater than efficiency of the original panel. A skydiver jumps from an aircraft at time t equals 0 and falls vertically downwards. The variation with t of her velocity v is shown in figure 2.1. So this diagram, figure 2.1, right? Using figure 2.1, state the terminal velocity of the skydiver. The terminal velocity, this one. So this is the terminal velocity here. It is going to this one. Okay, 39. So the terminal velocity is 39 meters per second. By drawing a traceable line on figure 2.1, determine the accelerations of the skydiver at time t equals 90. Okay, I'm going to I'm going to create a strike line with touch, okay, touch this graph on this point on, this is 9. So it's like a 9 second. Okay, here, this one, 9 second. It's 9 because 5, 6, 7, 8, 9. This one 9, this one 9, and this is 9. Touch in 9. Okay, the strike line. Now the strike line through this coordinate point and this coordinate point. This coordinate point is 37. Sorry, not 37, 9. Oh, wait, I have to check first whether 9 or not 9. Probably 11. 11. This the coordinate point 11, comma 37, 11 and 37. While this coordinate point, when I check, it is 7 and 33. 7, 33. Okay. So velocity equals gradient, that is 37 minus 33 over 11 minus 7. And it is 4 over 4 equals 1. So the gradient equals, or the velocity equals 1 meter per second. Here. Acceleration, sorry, not velocity, acceleration, the acceleration. I mean acceleration, not velocity. Because yeah, acceleration is equals delta Vt over delta T. Yeah. And it is same with if you calculate the gradient M. So this one, the calculation. Next. The mass of the skydiver and her equipment is 68 kilograms. The upthrust on the skydiver is negligible. After reaching terminal velocity, after reaching terminal velocity, okay, the skydiver opens her parachute at time t1. A total drag force of 1,800 newtons acts on the skydiver. Determine the magnitude and the direction of the accelerations of the skydiver at time t. So we're going to determine acceleration as well direction. Right. Uh, Force. First, we are going to calculate force. Total force. Total force is 68 because it mass. It's one mass of the skydiver. So we have to multiply by gravitational force 9.81 minus 1,800. Okay. And it's because total drag force 1,800 newtons. And if you calculate, the result will be minus 1,133 newton. Now, acceleration. For accelerations equals total force over mass, or minus 1,133, this one, over mass is 68, and the result is minus 16.66, and approximately 17 meter per second squared. So the solution is 17. And directions. Oh, directions, because it's minus, so direction to upwards, because minus. The parachute is fully open at time t2, fully open. At a later time t3, the skydiver reaches a constant velocity of 5.7 meters per second. Describe and explain the variations with time of the magnitude of her acceleration between time t2 and time t3. So between t2 and t3, between t2 and t3, I mean, the drag force will be decreased. Okay. So drag force will be decreased. Why will be decreased? Because its speed decrease. Yeah, due to its speed decrease de decreases. Okay. So the resultant force will be decreased. Okay, so decreases. Okay, and uh, regarding acceleration, her acceleration and her acceleration, the acceleration decreases uh, will be decreases into zero. Okay, and decreases and being zero. More and more, it will be zero. Calculate the change in momentum of the skydiver between T1 and T3. The formula of momentum delta P equals M times velocity minus the initial velocity. So 68 times 5.7 minus initial velocity 39. Initial velocity is 1. Because now we determine this one. Okay. That is the terminal velocity. Yeah. So if you calculate, the result is 2,264.4. Okay. And approximately becomes 2,300 Newton second. So this is the momentum. Minus meaning the direction. Okay. But the momentum is 2,300 Newton second. Number 3, lightning occurs when charge builds up in the atmosphere, creating a potential difference between the ground and the atmosphere. During a lightning strike, there is an average current of 3.3 times 10 power 4 A, 3.3 times 10 power 4 amps, because this is the average current for a time of 2.6 times 10 power minus 5 seconds. Calculate the charge transferred during the lightning strike. I'm going to using this formula. Q equals I times T. It means Q equals I equals 3.3 times 10 power 4, while T is 2.6 times 10 point minus 5. So it's going to be, if you calculate, it is 8.58 times 10 power minus 1, because 4 minus 5. And the result is 0.858, or approximately 0.86 Coulomb. So charge is 0.86 Coulomb. The potential difference between the ground and the atmosphere is 3.10 power 7 volt. Calculate the average power in gigawatts transferred during the lightning strike. Okay. So to calculate power, I'm going to using this formula. P equals I times P. Current times potential difference. So it is, I is potential difference just now 3.3 times 10 power 4 amps. And potential difference is 1. Okay. 3.0 times 10 power 7 volts. And if you calculate, it becomes 9.9 times 10 power 11 because 4 plus 7 times 4, it is watts. It's going to be 990 times 10 power 9. And this is giga. So it is 990 gigawatts. That's the result. A lightning rod is attached to a tall building to conduct charge safely to the ground. The lightning rod is modeled as a uniform cylindrical copper cable of a total length 95 meters that runs from the ground to the top of the building. Okay, from the ground to the top of building, as shown in figure 3.1. Okay, so this is the lightning rod from the ground to the top of building. Question. The resistance of the lightning rod is 9.6 ohms. The resistivity of copper is 1.7 times 10 power minus 8 ohm meter. Determine the radius of lightning rod. All right. Area of that rod is, the area is pi r squared. Okay, while the formula is r equals rho times L over A, length over A. And we're going to find this one, R. So uh, I will arrange this formula being rho times L over pi R squared. Now we are going to arrange this formula becomes R is the subject. So it means R squared pi R first. Pi R equals rho times L over R, resistance. This is resistance, R for resistance. So it means R squared is rho times L over pi R. And R, I'm going to move here, square root pi times L over pi, rho times L over pi R, pi times resistance. And it's going to be, rho is 1.7 times 10 power minus 8 ohm meter times L is 95. 95 length. I'm going to show you 95 according to the information that this one. Total length is 95 over 22 over 7 times resistance is this one, 9.6. 9.6. And if you calculate, it will be 5.352746 times 10 power minus 8. And it is, calculate this, becomes 5.352746 times square root uh, 10 power minus 4 squared. Square root of this decimal number is 2.3136, while this one is 10 power minus 4, and approximately becomes 2.3 times 10 power minus 4. The result here, 2.3 times 10 power minus 4. Now, the radius of the copper lightning rod is double with no charge, with no change, with no change to its length. Okay. Double. Okay. The radius being double and the length no change. State the effect of this change on the resistance of lightning rod. Of course, the resistance will be decreased. Okay. Its resistance will be decreased. Yeah, decreases. Its resistance decreases. Right. But D. A section of the lightning rod of length is 0.12 meters is removed for testing. A tensile stress of 1.9 times 10 power 6 Pascal is applied as shown in this figure 3.2. Okay, tensile stress, length 0.12 meters. The sections of the rod obeys Hooke's law. The Young modulus of copper is 1.3 times 10 power 11 Pascal. Calculate the extensions of the section. Extension, okay. I'm going to use this formula that extension equals sigma over epsilon. So I'm going to add that this formula here I will discuss here regarding this formula that E equals sigma over epsilon, and it is actually x. X is with I mean this epsilon is E equals L over X as well. Why? Because E equals E equals epsilon, equals 1 over X over L. That's one. So that's why we got this one. So it means the implication we can arrange this formula becomes X plus sigma times L over E, this one. Yeah. So it means, wait, we can determine X that 1.9 times 10 power 6 times 0.12 over 1.3 times 10 power 11. And if you calculate, it becomes 0.1754 times 10 power minus 5. And you can simplify, becomes a decimal 1.754 times 10 power minus 6. And you can convert, one round off becomes 1.8. 1.75 becomes 1.8. 10 power minus 6 meters. So this is the extension. 1.8 times 10 minus, sorry, 10 power minus 6, or minus 16, minus 6 meters. That's the unit. A pinball machine uses a spring to launch a small metal ball of mass 4.5 times 10 power minus 2 kg up a ramp. The spring is compressed by 8.0 times 10 power minus 2 meters and held in equilibrium as shown in figure 4.1, this diagram. The ramp is at an angle of 15 degrees to the horizontal. The spring obeys Hooke's law and has a spring constant of 29 Newton meters power minus 1. Calculate the elastic potential energy in the compressed spring. So elastic potential energy is half kx squared. Okay. K is, it's 129 Newton meters per second and Newton per meter, while x is 8.0 times 10 power minus 2. It's 1. Yeah, that's 1x. So we can calculate, substitute, the number becomes half times 29 times 8.0 times 10 power minus 2 squared. And if you calculate, the result will be 928 times 10 power minus 4. Becomes 9.28 times 10 power minus 2 joule. Or you can we have you can approximately becomes 9.3. Yeah, 9.3. 9.3 times 10 power minus 2. That is elastic potential energy. Next, the spring is released and expands quickly back to its original length. Okay. Calculate the increase in gravitational potential energy of the ball when the spring returns to its original length. Okay. Increase in gravitational potential energy. Right. This potential energy increase in gravitational potential energy, it means delta. So delta uh, potential energy, the formula mgh, but h as well delta. And then for m given 4.5 times 10 power minus 2. Okay. Now I'm going to discuss about uh, delta H first before we continue to calculate the increase in gravitational potential energy of the ball when the spring returns to its original length. Okay, so the ball will be this. I'm going to show you this um, triangle, right angle triangle. Okay, this condition. So this is 15. So I'm going to sketch here. This is H, delta H, okay? And this is ball position here. And this length is 8 times 10 power minus 2 meters, okay? And this is 15. So sine 15 equals delta H over 8 times 10 power minus 2. So it means delta H equals 8 times 10 power minus 2 sine 15. We are going to use this delta H. So wait. All right. So so potential energy, delta potential uh, energy equal mass is this one, 4.5 times 10 power minus 2 multiply 9.81 gravitational force, and delta H is 8.0 times 10 power minus 2 sine 15. And the calculation will be 353.16 times 10 power minus 4 because minus 2 plus minus 2. And sine 15 is 0.2588. And if you continue to calculate, the result will be 91.4045 times 10 power minus 4. And next, the calculation will be 9.14045 is 10 power minus 3. So from 91.4045 being 9.14045, 10 power minus 3, or approximately becomes 9.1, 10 power minus 3, 9.1, 10 power minus 3 joule. Let's continue. The ball leaves the spring when the spring reaches its original length. Okay? Assume that all elastic potential energy of the spring is transferred to the ball. Calculate the speed of the ball as it leaves the spring. We're going to calculate the speed, meter per second, the units. All right. To calculate the speed, to I'm going to using this formula, but kinetic energy is half mv squared. So let we arrange this formula being v is the subject. So it means v squared equals 2 times kinetic energy over m. And v equals square root of 2 times kinetic energy over m. So it means v equals square root 2 times. Okay, I would like to discuss kinetic energy first. The kinetic energy is total E minus delta potential energy. As you know that the total E is 9.3, sorry, 9.3 times 10 power minus 2 minus 9.1 times 10 power minus 3. Total E, I'm going to show you this. Total E, this one. E, 9.3 times 10 power minus 2, while potential energy is 9.1 times 10 power minus 3. Okay. So it means in brackets with 2 multiply 9.3 times 10 power minus 2 minus 9.1 times 10 power minus 3. Mass is 4.5 times 10 power minus 2. And if you calculate it, it is 3.72889. And the result is 1.93 meter per second. So 9.3. See, the ball comes to rest on a horizontal trapdoor of negligible mass, okay, at a distance d from its pivot. A force F acts vertically downwards at a distance of 2.0 centimeters from the pivot, as shown in figure 4.2. So this is a diagram. The trapdoor is in equilibrium when force is 1.7 Newton. Calculate D. Or D in meters, the unit in meters. So, this one, I'm going to give name D1. D1 is, the unit is in centimeters. So we have to convert from centimeters to meters. So D1 is 2 centimeters. It means in centimeters, we have to convert 2 times 10 power minus 2 meters. Okay, this is the one conversions of this number. Okay, I'm going to using this formula F times D1 equals m times G times D. And if D is the subject, we can arrange like this. F times D1 over M times G. So D equals 1.7 times 2 times 10 power minus 2. Okay, this is F. D1, this one. It is, just now we convert from centimeters to meters. And mass is 4.5 times 10 power minus 2, while gravitational force 9.81. And I'm going to continue to calculate. D equals, this is 3.4 times 10 power minus 2 over, calculate 4.5 times 9.81. And that is 44.145 times 10 power minus 2. Divide becomes 1. And the result is 0.077. And we can convert, become 7.7 times 10 power minus 2. So D is 7.7 times 10 power minus 2 meters. Force F is decreased from 1.7 Newton. State the directions of the resultant moment about the pivot on the trap door. The direction is clockwise. Why clockwise? Because if you look this diagram, okay, F, okay, F is 1.7, so 1.7, 1.7, while this ball, okay, let's see, this ball mass is 4.5. This ball mass is 4.5 times, wait, I'm going to check first. Okay, yeah, 4.5 times 10 power minus 2. So that's why it will be clockwise. Yeah. Number 5, state Kirchhoff's second laws. Okay, the law, the law state that the sum of electromotive force equals the sum the sum of electromotive force equals the sum of potential difference. The sum of electromotive force equals the sum of potential difference on around here, a closed loop. A battery of electromotive force 9 volts and negligible internal resistance is connected in series with a variable resistor X and a thermistor Y. Okay, as shown in figure 5.1. So this is thermistor and this one is resistor. Okay. Figure 5.2 shows the relationship between temperature and resistance for the thermistor. Okay. Thermistor is Y. Question. The current in the circuit is 1.1 times 10 power minus 2 amps. The potential difference across Y is 4 volts. Calculate the resistance of X. Right. Uh, to calculate resistance, we are going to using this formula V over I. Resistance equal V, or potential difference, over I. Okay. So it means resistance, total potential difference is 9 minus 4. So it over 1.1, because the electricity current is 1.1. This times 10 power minus 2 amps. And it is 5 volts over 1.1 times 10 power minus 2 amps. And the result is 454.545 ohms. Approximately becomes 455 ohms. The resistance is 455 ohms. Next, the temperature of Y is changed to 190 Coulomb. 190 Celsius, not Coulomb, because temperature. The resistance of X remains unchanged. Determine the new potential difference across Y. Okay. First, we need to determine the resistor or the resistance, or the resistance across Y through this graph. This is a graph for thermistor for Y. And the temperature is 190. 190, it means this is 5, 1, 2, 3, 4, 5, 6, 7, 8, 5, 6, 7, 8, yeah, 9 here. Yeah. This is 190, so it means this one is 25. Okay. All right. So the resistance is 25. Ry is 25 ohms. And total resistance is Ry plus Rx. Resistance in thermistor and resistance in resistor. Okay. So it means R total is 25 plus 455. Yeah, this one. So it equals 480 ohms. Okay. And we are going to determine electricity current, line V, because total potential difference 9 over 480 ohms, 0.01875 amps, or 1.875 times 2, times 10 power minus 2 amps, or approximately becomes 1.89 times 10 power minus 2 amps. And let's be determine the potential difference. Potential difference equals I times Ry, potential difference across Y. Okay. So it is 1.89 times 10 power minus 2 times, this is the electricity current times Ry is 25, and it equals, let me calculate first. Yeah, this one, 0.46875 volts. Or you can approximate becomes 0.47 volts. 0.47. The resistance of X is increased. Okay, Rx increase. The temperature of Y remains at 190 degrees Celsius. By reference to the currents in the circuit, state and explain the effect of this change, if any, on the potential difference across Y. Okay. The frequency of sorry, this is the resistance. If Rx or resistance X increase, if Rx increase, okay, if Rx increase, it means the implication uh, for total total resistance as well will be increase. Okay, why? Because if you look the formula, X plus R Y. If this one increase, okay, Rx increase, implication for this number. If this number increase, the result will be increase also. So yeah, what else? After that, yeah, I would like to explain. Yeah, if V equals R times I. Okay, so if current decrease as well, potential difference also will be decreased. If current or I decrease, decreases, potential difference decreases. Okay. Yeah, including potential difference across Y. Potential difference across Y as well decreases. I think clear. Okay, students. Let's continue to number 6. Like of a single frequency is incident normally on a diffraction grating, and interference patterns of bright and dark fringes forms on the semicircular screen shown in figure 6.1. I have explained this material on our classroom, so but I would like to re-explain regarding these problems. Okay, and just a reminder to you. The light has wavelength 520 nanometers. The separations of the lines in the grating is 3.8 times 10 power minus 6 meters. Determine the total number of bright fringes formed on the screen. Okay, so the formula is d sine theta equals n lambda. D is distance between between the yeah between the like, okay, wait, not the like, between the slits is, if I'm not mistaken, wait, yeah, the distance, d is the distance, and then theta is the angle of the fringe, and is the order. I have explained this. N is order on the fringe, then lambda is wavelength of light. Okay, so now we're going to find N. So we have to arrange this formula becomes N is the subject. It would be like this, d sine theta over lambda. So it's going to be N d equals 3.8, sorry, 3.8 times 10 power minus 6 sine 90, okay, over 5 520 nanometer. It means times 10 power minus 9. And if you calculate, the result will be 7.3076. Approximately becomes 7. So that is 7. The light is replaced with red light and with red light of a single frequency. State whether the frequency of the red light is greater than, less than, or the same as the frequency of the original light. Okay, so the frequency, uh, this frequency. So the frequency of red light, I would like to write down here the frequency of red light, okay, is less than frequency of original like. Yeah. The frequency, and as I explained in classroom, that the frequency and wavelength actually they have an inverse an inverse relationship. Again, frequency and wavelength of light, they have an inverse relationship. Inverse relationship. What it means? If frequency increases, wavelength would be decreases. Okay. Uh, for red light, the condition like that. If a red light has longer wavelength, but it has less frequency. Okay. I'm going to explain here, or part two, state and explain the effect of this change on the number of bright fringes formed on the screen. A calculation is not required. Okay, red light. I will, uh, I will write here the red light. This is red light. Red light has longer. Yeah, I'd like to using a red light. Okay, for my explanations. Red light has longer wavelength, but less in its frequency. Yeah. So the implicated to so a number of bright rings. Sorry, number of bright fringes uh, also form is less. Sorry, form is less. Students, you have to learn deeply regarding this material. Next, number 7, the last question. A particle Q and a particle R is composed of one quark and one antiquark. State the name of the class group of particles that includes Q and R. In my classroom, I have explained regarding the difference between quark and antiquark, and we have been discussed about this material. So, but I will answer, I will solving this question, this part, and then I'm going to continue discuss this material on my lesson. So state the name of the class group of particles that includes Q and R. The name are mesons or meson or hadrons. Yeah. Mesons or hadrons. What is that? Hadrons are particles made up of two or more quarks. So how about mesons? Are mesons is a type of hadrons. Yeah, so actually mesons is a type of hadrons. Mesons is a type of hadron made up of a quark and anti-quark. Okay, so if hadrons made up of two or more quarks, while mesons made up of a quark and anti-quark. So that's the difference between mesons and hadrons. B, Q has a charge of 1e, where E is the elementary charge. R has a charge of 0. Complete table 7.1 to show a possible second quark in each of Q and R. All right, this is table. If look, this is Q, this is R. Q has minus 1e, while R has 0e. The first quark type of Q is strings. So it means the second quark of Q is should be anti-up. Okay, anti-up. So about R, if R charge 0, so its first quark is anti-up. So the second quark it should be up. Okay, anti-up and up. String anti-up.